Okay, so this is the 32nd lecture. This is we will continue from the last lecture. We stopped at the last lecture at the proof of this. We wanted to show that this is already we have observed that the product of pk pi is divided the minimal polynomial. Now, we would like to show the other direction, that is this and by showing this is an annihilating polynomial. So, to show an annihilating polynomial, we take a general vector v, decompose it as a sum of elements small w i's. Now, when I apply the operator here, so pkt when it comes here, it vanishes the term wk. Now, so this is this. Now, when this pk minus 1 t will appear, then it will not we do not know what it is going to do with this other terms, but for sure when it comes here, then we will have pk minus 1 t of pkt times pkt wk minus 1. When pk and pk minus 1, they will pkt and pk minus 1 t will commute. So, we will have pkt compose pk minus 1 t applied on wk minus 1, that term will go. Therefore, if you keep on going that, all the terms will be 0. Hence, this is an annihilating polynomial. So, therefore, we see that this is the minimal polynomial. So, again try to explain that. Let me try to explain what this theorem says. It says, suppose you have a decomposition into non-trivial invariant subspaces and you know the minimal polynomial on every the minimal polynomials on each of these direct summands, and if they happen to be irreducible, happen to be mutually co-prime, then the minimal polynomial of t is going to be the product of the minimal polynomials. Okay. And the key thing is this, I did not prove this is, but you should realize that f is a factor of h, g is a factor of h, and there is nothing between f and g which is common. So, both f times g should be there. Okay. Okay. So, this is exactly same as that of integers. I did not prove it. I am leaving this for you to prove. Anyway, so we should go ahead. Yeah. So, in view of this theorem, from 3 to 4 is now clear, because the minimal polynomial on each v lambda is just t minus v lambda is t minus lambda. So, therefore, for different lambda and lambda prime, t minus lambda and t minus lambda prime are co-prime to each other. Therefore, the minimal polynomial for t is the following. Now, we will prove the reverse direction. For that, again we will prove a very general theorem. What should be the theorem that we are expecting to prove? The theorem is as follows, that so I mean, what are we doing? We are going to prove 3 from 4. So, we have this. So, from this we are supposed to get the decomposition. Okay. Now, what is the first? Let us say, so we are from this we want to prove that v is v lambda 1 direct sum v lambda k. Okay. So, remember that what is v lambda 1? This is nothing but kernel of t minus lambda 1 I. Similarly, kernel of t minus lambda k I. Okay. This is what we are going to see, and that is something interesting. So, try to see. So, we have this, this polynomial is a product of this, and any two such factor is co-prime to each other, and what you are having is, so v is admits the decomposition, the following decomposition, that is the direct sum of kernel of each of these factors. That is what we are seeing here, and we are supposed to prove here. So, the theorem that we intend to prove in the generality is as follows, that let f equal to p1 p2 pk. Okay. These are all polynomials, these are all polynomials p1 p2 pk, and gcd of pi pj is 1 for all I not equal to j. Then we must have kernel of f t is equals to the kernel of direct sum p 1 t kernel of p k t. In fact, we will prove something more furthermore. If is T invariant and contained in the kernel inside the kernel of T, then W we will in fact prove this. Okay. We will prove this first. So, try to observe that if we can prove this, in view of that the 4 implies 3 becomes immediate, right. Fine. Okay. So, let us try to prove the first part. In fact, that motivates us how to prove the extension of that. So, yeah, we can erase this. Okay. So since each pi pj is for 2 distinct pi pj's are co-prime. So, in view of that if we define pi bar t is nothing but the product of all pj's except j not equal to except the I. Okay. So, we took the product of all pj's except the ith one, call it pi hat j, then pi hat j and pi they are co-prime. Okay. Now, what can we further? So, we have to start with something, we have to start with a member in the kernel of f, write it as the member of sum of kernel of this plus something something kernel of that. Okay. Now, what can we further see? So, when can I say that something lies in the kernel of P? What type of elements are assured to be in kernel of P? If you remember, if the element is of the form, let us say P2 t plus pkt times V. So, such elements are surely, so if V lies in kernel of F, then such elements are surely lying in the kernel of P1 t, because if you are calculating P1 t, the kernel f t it will be 0. So, that motivates us that we should rather look for the following, that P1 hat up to Pk hat. So, there is no common factor which divides all Pi hats, right. There is no common factor that divides all Pi hats, because for example, I mean try to see if there is a factor that divides Pi, that all Pi hats, then I mean for example, let us say for 2, suppose the situation is P1, P2, P3. So, one is P1, P2, the second one is P2, P3, the other one is P1, P3. Okay. So, if there is any factor at all in irreducible polynomial, because you can always talk about every polynomial is a product of irreducible ones. So, what is an irreducible polynomial? Let me recall for you. So, I assume that you are well equipped with the polynomial. So, polynomial is irreducible if it does not admit factorization such that both the factors are non-constant. Okay. This is more like this is analogues of prime numbers. So, that is also another right. So, every polynomial the way you prove that every number is a product of primes, in the same way you can prove every polynomial is a product of irreducible polynomials. For example, over C the only irreducible polynomials are the linear polynomials. Over R x square plus 1 is indeed a quadratic irreducible polynomial, because if this is irreducible then it would have been split over R, and that is not possible because it does not have a root in R anyway. So, if something divides all of them, then from which is very easy to see at a contradiction, because for example, the irreducible polynomial, if this is H, then irreducible polynomial whenever it is dividing a product it has to divide one of them. So, for example, here if H divides P1 and H divides P2, then I mean if it divides both of them, I mean it is very easy to look at. I am just trying to explain you by a very special case that why the GCD is 1. So, suppose H divides all of them, then what can you, then from that can you arrive at a contradiction? Remember that P1 P2 and P1 P3 only thing that is common is P1. So, therefore, okay, and also you have to yeah. So, each P1, so suppose H divides P1, then each H cannot divide P2 because P1 P2 they are mutually coprime. So, H cannot divide P2. So, if H cannot divide P2, then H has to divide P3, which is a contradiction, because any Pi Pj they are coprime to each other. So, the same argument goes for in the general case as well, okay, because suppose H divides P1 bar. So, in P1 bar P1 is missing, right. So, that means H must divide one of some other Pj's and exactly one Pj, and then you come to Pj hat, there it will be a problem, because it Pj factor is not there, it cannot divide others. Alright. So, since these are having 1, so from the general fact about polynomials that one can be written as a linear combination of them. So, we do have polynomials, let us say f1 p1 hat plus 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 fk pk hat equal to the constant polynomial 1, okay. Because the GCD is 1, it can be written as a combination, and that shows that P1 T, F1 T, these are compositions plus 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 if let us say Pk T. So, this we have proved this basic properties earlier is the identity map, okay. Now, the rest is very obvious. So, since this is identity, apply that on V. So, then each factor goes like this, then what is next? Try to see that. So, let me P1 T of F1 T V plus 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 Pk hat T of Fk TV equal to V, okay. And this part, certainly this part lies in the kernel of P1, because once you apply kernel of P1, so P1 T times composition P1 hat T will be exactly Ft, and I mean Ft composition F1 T is same as F1 T composition Ft, and FTV is 0, right. We have already observed that this kind of things surely, I mean a vector of this kind surely lies in the kernel of P1. I mean in general for any, if I drop the factor of Pi, then the product of the others, the composition applied on any vector from the kernel of F surely lies in the kernel of Pi. So, what does that show? That shows that every vector in the kernel of V can be written as the sum of vectors W1 up to Wk, each Wi lies in the kernel of Pi. So, that shows that this is the sum of the kernel of Pi's. I have not proved that the sum is direct, I just proved that this is just sum. So, let me write that is better. So, this shows, try to understand again, let me repeat the proof for you. This lies in the kernel of P1, and in general term Pi hat t times Fi t times V lies in the kernel of Pit, right. So, therefore, this shows kernel of Ft is nothing but the sum of kernel of P1t plus Pkt. Try to understand what motivates us to look for this is this, because we know that given any vector V, this kind of things always they do lie in kernel P1. So, therefore, and for a different I can frame different such vectors, and since their GCD is 1, I will have a combination of them to be identity, and I mean that observation tells me how to go ahead. And anyway, now we are supposed to prove that this sum is direct. How to show that the sum is direct? In order to show something is direct, sum of subspace is direct, what do you need to do? You need to first, so to show it is direct, to show this is direct, so assume W1 up to Wk is 0, where each Wi lies lying in the kernel of Pit, then we would like to show Wi is 0 for all I, right. That is what we have proved, that is enough to show some sum is direct, a sum is direct, this is what we need to show. Okay. So, that is again a trivial exercise, in fact I can do it, in fact it is easy to see. So, remember that each Wi, right. So, each Wi is in particular lies in the kernel of Ft, right, because all these are subspaces of, I mean all these are kernel of Pit is a subspace of kernel of Ft, okay. That is an immediate one, because kernel Pit, then you apply P2t up to Pkt on that, and that becomes Ft. Okay. So, since it lies here, so I mean you do this for V equal to Wi, right. So, once you assume V equal to Wi, once you do it for V equal to Wi, this is what you get. Okay. Now, remember, let us say here, suppose I not equal to 1, right, I not equal to 1, then what do you get? I not equal to 1, that means here like in the P1. So, try to understand, if you investigate just one term, it will be quite clear, P2t up to Pit Pkt of Wi, okay. This is what the first term is. Since I not equal to 1, Pit is present in here, that means, so what is this? So, this is same as you can pull Pit here, and Pit from this assumption becomes 0. So, therefore, you see that, so more generally if you see that Pj hat t times I mean composition Fj t Wi is 0 if I not equal to j, right, yeah, if I not equal to j, fine. So, all right, then what do we get out of that? Uh, First, I mean, as soon as Wi is present, things will vanish. That is pretty sure. Okay, as soon as Pi is present, terms will vanish. The only problem might happen at when the Pi is not present. Okay, Pi is not present. Okay. So, we want to show that each Wi is 0, right. Then what to do? Each Wi is 0 when Pit Fit Wi. So, therefore, Wi is okay. So, that forces us here, if we go right here. So, except the ith term, all terms vanish. So, we had Pit Fit Wi is Wi, if I am not wrong. Okay, fine. So, now what can one do here? What can one do here in order to show this each Wi is 0? So, we know that once we this lies in the, so okay, are we going in the appropriate direction? Let me first ensure that if this is 0 and Wi is the kernel of Wi, in order to show let me go by each of these terms, that is better. Well, since I get stuck, let me do the case for try to get the idea how to prove it in generality. Let me do the case for that P1 P2, then that will actually help motivate me to look in generality. So, let us see if for the case P1 equal to P2, I mean for the case only two polynomials P1 P2. Okay. So, we have P1 Q P1 Q1 plus Q P2 Q2 equal to identity. Okay. So, therefore, for any vector, so P1 Q1 V plus P2 Q2 V equal to V, where V lies in the kernel of F, V lies in the kernel of F. Therefore, this lies in the kernel of V, this lies in the kernel of P1, this lies in the kernel of P2. So, that part is there, and now suppose V is written as W1 plus W2, then what do we wish to see? So, let us better to see that for two functions, two polynomials, then it will help me. So, if this is 0, we would like to show that the other one is 0. So, W1 is indeed P1 Q1 W1 and P1 Q1 W1 and then P2 Q2 W1. Okay. So, this part automatically goes away. Now, P2 Q2 W1 equals to W1 for all W1 okay. Now, what does that give me? Why is that troubling a lot? Because all right. So, let me work it out here, then that will be helpful. P2 Q2 W1, P2 Q2 W1, we have to show that this is simply that case P2 Q2 W1 W1. We have to show that W1 and W2 both are 0. So, W1 is to be shown as 0, W2 is also shown to be 0, P2 Q2 W1 that lies. So, that W1 equal to P2 Q2 W1, which is somewhat does that help me? Okay. So, one thing I must be missing here, look, like what I have written that goes for and here as well. So, W1 is certainly minus W2, does that help me? W1 is certainly minus W2, then okay. So, this lies minus W2 and that shows W1 is minus W2. So, P2 W1, no, the only thing is what I have just used here is the following, that I have never used here the sum is exactly this, right, because what I have done that I can do for any W lying in the kernel of PIs, I can do for any W that lies in the kernel of PIs, and therefore, I have not used it ever, I should use it somewhere. So, the question is how to use that somewhere. Well, now it is done. So, see here. So, earlier what we here as what we have got W1 equal to P2 Q2 W1, right. Now, what you do is very simple, write it as Q2 P2, T is there always, minus W2. Now, P2 W2, yeah. Now, just a minute, P2 W1, yeah. Now, P2 W2 will vanish, yeah. Actually, I was not using that anywhere. That will now, yeah. So, look at this term better. So, Pi hat T compose FIT, write it simply as, write W1 as the sum of other Wj's, right, j not equal to I. Now, when we apply for all j not equal to I, we see this will be Fi of T compose PIT of Wj, and PIT hat PJT term is appearing and Wj is coming from kernel PJT. So, this becomes 0, okay, done. So, yeah. So, this I mean like from this relation this is what we are getting, okay, and now we independently use this here, we see that this left hand side becomes 0. So, thus each Wi is 0, that shows the sum is direct, okay. Now, it is a perfect proof, yeah. The motivation is if you do it for when you get stuck, you just do it for the case of 2 operators, then it will be clear, okay. So, thus we have proved the sum is direct, the rest of the proof is all even more direct, that is. So, this part we have proved. Now, let us come to this part. If W is an T invariant subspace inside the kernel, so let W be in front W, then we have already proved for any V that summation PIT I from 1 up to k compose FIT W, right. Earlier we proved this for any V, right, any V like in the kernel, and we know that given W, these are the unique elements from this direct sum. Now, you have to observe the following, T T is invariant, W is T invariant. Therefore, this vector lies in W, right? This vector lies in W, okay? Because that's very easy, na? Because if you have a polynomial a0 plus a0I plus a1t plus an t to the power n, then you apply that on W, since T, therefore what will you have? T w, for any W, T w goes inside W, therefore T square W also goes inside W from the T invariance. So, you see that this lies inside W as well for any polynomial. So, therefore, yeah, better that you put it in this way. So, thus in the W, the constituents they all, so given W, you know that it can be written uniquely as the sum of elements from here, here and there, and in fact these are the elements, the direct sum shows the uniqueness, and you see they also lie inside W as well. So, therefore, that establishes this inequality, the equality. Try to understand that given W, I know that these are the unique elements from for any I, this is the unique element from kernel Pi such that here sum is W, okay, that I know, and furthermore we see that also lies inside W. So, given W, its constituents they also lie in one hand inside the kernel Pi and on the other hand inside W. So, therefore, the intersection, the rest is now the rest is done. Okay. So, we have proved this general theorem, and in view of that this is now obvious because yeah, in view of this theorem the 3 goes to 4 is in fact triviality, because kernel of MTT will be V, is an annihilating polynomial equal to direct sum of kernel of T minus lambda 1 I plus process T minus lambda k I, these are precisely VKs. So, now we have proved the equivalence of all 4 statements, okay. Fine. Now, I will show you some further consequences of this general one. Yeah. So, basically thus we have before going into the consequences, we have, let me just remind you that these are the all 4 equivalent criteria for the diagonalizability of an operator. So, the 4th one becomes very simple. I mean, sometimes what happens that, I mean, it becomes easier for us to get the minimal polynomial by means of some decomposition. We have already seen a theorem that if you have a decomposition and from the I mean the minimal polynomial on each of these factors, you can constitute the minimal polynomial of the whole operator on V. So, suppose we have get a decomposition on to the direct sum of Wi's in on the restriction of 1, we see there is a repeated root, then from that immediately we can conclude T is not diagonalizable, okay. I will show an immediate so you can see that this is just the second part is just an extension of the previous one. I will do an important consequence of the second part. I will prove 2 important results regarding diagonalizability. So, the first simple is if we have proposition, we will prove diagonalizable operators are semisimple. Semisimple. What do you mean by semisimplicity? This means the following, that if, so earlier what we have proved is if W is a subspace of V, then there is an invariant complement of W. Now, semisimply suppose my W is T invariant, I want a T invariant complement. So, if W is T invariant, whenever W is T invariant, there exists another W prime which is T invariant and of course complement, otherwise it does not make any sense. Okay. So, try to understand when T is when V is a general vector space, I mean of course finite dimensional and W is a subspace, we know that there is a W prime such that V equal to W plus W prime, and there are plenty of such V's. But if further we insist that T is V, further we assume that W is T invariant and the W prime, that also if we insist that to be T invariant, this may not be the case always. For example, example of let us say a non semisimple map is the one that I have just given you, x comma y goes to y comma 0. Okay. So, here if W you choose the x comma 0, you cannot have a invariant complement, because why? Because you have an invariant complement, then that would be, I mean this is a one dimensional, so the complement will be one dimensional. So, invariant one dimensional subspace, that means you should have an that will be, you will have an eigenvector here, but we have already proved that there is no eigenvector other than those which are lying in the x axis. Okay. So, let us see, so I mean when you further insist that the W prime is given W prime is T invariant, given W is T invariant, W prime will be T invariant, then it does not happen always. This is one example. But this example, we have already seen that this example is not a diagonalizable one. So, this proposition says that if the map is diagonalizable, then it has to be semisimple. Now, why so? That is very easy, that given, so since this is diagonalizable, then what you can have is, so you write proof. So, the minimal polynomial, since diagonalizable, minimal polynomial must be of this form, right, and lambda is a distinct, and in particular you should have. So, therefore, using this theorem, W becomes the direct sum of W intersection kernel of, so W intersection kernel of T minus lambda I. Okay. Or if you can write it by Vi, W intersection Vi. Okay. Now, the interesting part is on Vi, and what is the linear restriction, I mean what is the restriction of T on each of the Vi's? Vi is an eigenspace, so on Vi this is just scalar multiplication. So, what you do is for each I, okay, for each I this is a subspace of, for each I you have a, I mean let me be very somewhat explicit, choose a basis of Bi of W intersection Vi, okay, and extend it to a basis of Vi. So, you can just simply assume that Bi and union, let us say the extra vectors that you are adding to Bi, let us call the, let us denote their collection by Bi prime, is a basis of Vi. Okay. Now, that is good, right? And then what you define is, let me write here, then what you define is, So, you take the linear span of B I prime, let us call it W I prime. This W I prime is claim W I prime is T invariant. Why? That is very easy to see, because W I prime is a finite linear combination of B I primes. So, when we apply T on such a combination, it will again be a combination of, because each vector on B of B I prime, when you apply T, this will be a scalar multiplication of that vector. So, any linear combination of B I prime, when you apply T on that, it is again going to be a linear combination of B I prime of right, because on every vector in B I prime the linear map acts as a scalar multiplication. So, thus W I is T invariant. Therefore, we have the following that each V I can be written as W I V I direct sum W I prime. Okay. Therefore, finally the choice of W prime will be the, so try to understand W I primes, right, corresponding to each I you have this W I prime, right, and when you take their sum, so the sum of these will give you W, and the direct sum of course the sum has to be that the sum of W I primes they have to be direct, because all of them are contained inside V I prime whose sum is already direct. So, the sum of the remaining, that is this W I primes, is going to be W prime. Since each W I prime is T invariant, W prime is T invariant. Okay. I hope, try to again quickly talk about the proof once again, then I will go ahead. So, we use that result to come at this level. Now, this is a subspace of V I. So, we start with the basis of the subspace and extend that to a basis of V I, and the extra elements that we have added, we consider their linear span, since each of these extra elements are eigenvectors. So, therefore, any linear combination of them will lie, any linear combination of them, when we apply T on that, then it will again a linear combination of those vectors. So, therefore, that shows each W I is T invariant, and now the sum of W I primes, that is going to be certainly T invariant, and this is W plus W I prime is certainly V, because W is direct sum of these, okay, and direct sum of V is V. So, therefore, the direct sum of this, which is W I prime, it must be the one which you are looking for. I repeat. So, if you want me to write, I can write. I do not need to use this. So, W plus W prime. So, yeah, W plus W prime, because when I say, for any vector space W1 plus W2 is same as W2 plus W1. So, the sum in which it does not matter, and direct sum is of course, after all it is a sum with some further property. So, the object is sum. So, the order does not matter. So, therefore, what you can do is, so W in one hand you write W as V I, and on the other hand, so this is from 1 up to k, on the other hand you have W I primes. Okay. Now, you club this W I prime with that, and that will give you V I, and the sum of V I's, direct sum of V I's will be V. Okay. I need to go ahead, and then the final one that I am going to prove is simultaneous diagonalizability. With that I will finish diagonalization, simultaneous diagonalizability. So, the theorem. So, suppose A and B are linear operators and they are commuting, then there exists a common eigenbasis. There exists an eigenbasis B, a eigenbasis common to both A and B. Okay. So, try to understand that individually A and B might be diagonalizable, for which you might have some eigenbasis. For B there could be some other eigenbasis, okay. But what I am saying that you have a single eigenbasis for both the operators A and B. So, that with respect to the that eigenbasis, when we write down the matrix for both A and B, the matrix will be diagonal. The diagonal matrices could be different. I mean, when you reduce A to the diagonal form and B to the diagonal form, they can be different, but the eigenbasis is same. Well, I will quickly give you a sketch of this proof. So, okay, so lambda is an eigenvalue of A. Since this is diagonalizable, we have this decomposition. Similarly, we have the further decomposition V lambda mu. Well, lambda is an eigenvalue of B, and let me just V lambda mu be kernel of B minus mu I. Okay. Now, it is very easy to see that what I am going to say is, I am leaving this to you to justify that kernel A and B commute, therefore, A B minus lambda I and B minus mu I and A minus lambda I, they also commute. A minus lambda I, B minus mu I equals to, for any two eigenvectors, eigenvalue lambda of A and mu of B. Therefore, try to understand that the kernel of this is kernel and image of this is going to be invariant under that, and vice versa. So, therefore, it shows that V lambda mu is nothing but V lambda intersection V prime mu runs over lambda, okay. Because of this, all right. So, what I am saying is B commutes with, I mean, for any scalar A, B lambda and mu, not necessarily even eigenvalue, these two operators commute, okay. And therefore, it shows okay. It is a huge, I mean, we have earlier this was the decomposition, we have further decomposed each V lambda like this. So, this is what we have, and this is, of course, this has to be V. Now, what you know what to do, you choose a basis of each of these pieces and their union will be a basis of V, and what about the, I mean, like any basis of, let us say, V lambda intersection V mu. So, any basis here, the vectors in that basis are eigenvectors of A with respect to eigenvalue with eigenvalue lambda, and as well the eigenvectors of the operator B with respect to the eigenvalue mu. So, therefore, if you choose any basis here, these vectors are both eigenvectors of A and B, possibly with different eigenvalues, and therefore, when you take their union, that basis, all the vectors lying in that basis are both eigenvectors for A and eigenvectors for B as well. That gives you an eigenbasis. Okay. So, try to understand the proof. The proof is, try to understand the proof. The proof is very, in a sense, natural one. So, like V mu lambda. Okay. So, this is the kernel of B minus mu I, mu prime I. Okay. So, the kernel of that is certainly invariant under, what I am doing is I am using this. Okay. So, it is certainly T invariant, A invariant, because So, as I said, for any two lambda and mu not necessarily eigenvalues, in particular if you take lambda equal to 0. So, you get A commutes with this. So, therefore, the kernel of this is invariant under A. So, therefore, this is an A invariant subspace. Using that, it will be the intersection. Now, you have the intersection of all of this you get this. So, therefore, what we have is we have chopped this each v lambda into several other parts, and chopped is in the sense of direct sum decomposition. And if you take basis of any of these pieces, each of these pieces and take their union, you will get it. Okay, I think I am done with diagonalization. Next topic that we can start is well, of course, there are several other results regarding diagonalization, for which I need the notion of inner product. So, I will come to that later. So, maybe in the next lecture I will either I can start with inner product or I can start with determinants, and if I do determinants, then after determinants I can prove further results regarding, well, diagonalizability I cannot say further because the criterias are over, for equivalent criterias. I can then talk about the situation when I cannot make it into a diagonal form, but however then I can try to bring it in the next simplest form that I can do. So, if I do it determinant first, then I will go for that, prove the Jordan, do the Jordan canonical form, existence and uniqueness, then I will come for inner product, or I can directly start with inner product and go further regarding diagonalizability of or the structure theorem for normal operators. Anyway, let us see. So, for this lecture I think I am done. I should just remind you that this is what I have left to you as an exercise, that if A, f and g both divide H, they are polynomials, and GCD of f g is 1, then f times g divides H. Okay, so how can we think of proving that? As I said, that it goes exactly along the line of integers. Here you can try. So, the way it can be helpful to you is, so there could be some trick which I am missing, maybe g this equals to 1. Okay, so yeah, fine, and we have to use that f and g both are dividing H. Now, I will just both are dividing okay. So, we should prove that f g divides H, f g divides H. So, how to get f g? So, H should be f times some f prime, g should be H should be g times some g prime. Using them, how to prove f g divides H? I can have a little try. If that does not work, that is fine. These are elementary things. H f prime. All right. So, maybe I should leave it here because this is elementary and that you can do it. Somehow you have to use this, and maybe let me see if I can see something that can be done or not. Somehow I have to bring f times g. To do it for f times g, I need to somewhat multiply somehow multiply these f and g in both are anyway, as usual leave it. I can't exactly remember the trick which goes here, but however the proof should be different. So, yeah, you can try it in your own or just imitate the proof for the integers, that will help you here. Well, anyway, I will or can I think of something, f g if g if this like this, that is like that g. Well, let's leave it here. I think I can't remember the trick. Just as I said, you just imitate the trick from the proof for integers. Well, with that I will stop here. Thank you.